Good morning. I hope you're having a great day. I appreciate you being here. We're going to continue on talking about the last chapter of Chem 222. And this chapter will be quite a bit different from the last chapter, which was the kinetics chapter. And kinetics was like the study of speed. This chapter, the nuclear chemistry chapter, is going to be more about what happens right in the middle of the atom, which is the nucleus. Nucleus. It's better in chemistry. No, I'm just joking. The nucleus of the atom is where the protons and the neutrons hang out. And the space around the nucleus, this kind of like little blue kind of little dots right there, that's the electron space. And it's going to be one of those days. 99, all right, pop that back on. 99% of all chemistry, and basically every other chapter of Chem 221 through Chem 223 has been about what the electrons do. But what we're going to look at in this chapter now is the reactions in that middle part, the reactions of the protons and neutrons. So we're reviewing here some terms from Chem 221 just to make sure that everybody's up to speed. Chemists use this kind of system to designate the number of protons as well as the number of neutrons in an atom. And the right-hand side of the atom symbol we've used a lot. So like the upper right-hand side is where the charge go. And like in CO2, the 2 by the oxygen in CO2 tells you the number of atoms in the molecule. But we're going to focus more on the left-hand side now. The lower left-hand number is called the atomic number. That's the number of protons. And on the periodic tables in this room, all of the blue numbers are the atomic numbers. And then the upper left-hand number is called the mass number. And the mass number is protons plus neutrons. So in this version of boron, if you wanted to know how many protons there were, that's easy. You look right at the periodic table, the blue number up there, the 5, that's the number of protons. And then the neutrons, what you have to do is you take the top number and you subtract the bottom number. So this particular version of boron has 5 neutrons. So 5 protons plus 5 neutrons, 10 is the mass number. This is referred to as boron 10, and that's an isotope of boron. And all the elements on the periodic table have multiple isotopes. And an isotope, again, means that the lower left-hand number, the protons, is the same across the board. But the upper left number is going to change. The neutrons will change as you have a different isotope. So in Chem 221, we did a lot of stuff talking about boron 10 and boron 11. And both of those systems have 5 protons. The lower left number is the same. It's the upper left number which changes. How many neutrons do you think there would be in boron 11? 6, right on. You would take this number, which is like this number, the mass number. You always subtract 5 since it's boron. It doesn't matter what the isotope number is. You always subtract 5, and that will tell you the number of neutrons. So here's an example of a type of a problem we looked at in Chem 221. And this is a problem with 2 copper isotopes, copper 63 and copper 65. Now, in the real world, you almost always have a higher percentage of one isotope relative to the other. So copper 63 and copper 65 are both around, and the question is which one is more abundant. And this is a problem where the other number on the periodic table will be really helpful. So on the big periodic tables in this room, that's 63.546, that red number, which has multiple names, but let's call it molar mass for the ease. The molar mass will kind of give you a hint often as to which is the more abundant. And if you think about a number line between 63 and 65, 64 would be right in the middle. 63.5 is closer to the 63 than it would be the 65. I'll draw this out here. I like the number lines a lot for these. So if you see a problem like this, the 63 on the copper and the 65 are the numbers you want to use on the number line. And then the midpoint, of course, would be 64. And on the periodic table, 63.546, That's a number that's much closer to 63 than it is 65. That's one way, and an easy way to tell that 63 is more abundant. If you think about it in terms of averages, if you're an average kind of person, you must have more 63 to get this number, the average of all the isotopes, then you'd have this number right here. Questions on any of these? Okay. So knowing that then, we're going to start seeing some really cool things in this chapter. But knowing that the upper left number is the mass number, the lower left number is the atomic number, will help us as we go through. And there's a whole series of particles. One of them is not really even a particle, but we'll call it that anyway. And these are things that are kind of unique to this particular type of chemistry. An alpha particle is something we're going to talk about a lot. And if you've ever been to a birthday party and you took a helium balloon and you, hey, talk like a chipmunk. All right, sound effects not necessary. All right. Anyway, helium, normally when you ingest a little bit, makes your vocal cords get higher, and it's kind of a fun, cheesy thing. This is a type of a helium as well. But if you did, because you're tight, if you did this kind of thing, you'd like die. All right, so don't, if someone gives you a balloon of alpha particles, which would be stupid by the way, but anyway, yeah, don't ingest it, man. This is like supercharged helium, all right? This helium is many times higher in energy than a regular helium would be. So you can get by with ingesting a tiny bit of helium. It makes your voice sound funny. This is nothing like you'd want to do. So think about this as like a supercharged helium. This is like pretty crazy. Now, helium is number 2 on the periodic table, 2 protons. And almost all helium is helium-4. It's not 100%, but it's pretty close. So the helium-4 is what we would call this. And this is one way to represent this alpha particle in these reactions. But what's oftentimes used is the little Greek symbol for alpha, that little symbol right there. This is a way to show it. And if you're talking about a helium nucleus, this is not your grandmother's helium, all right? This is one you want to be really careful with, man, because this will cause lots of damage to your body. We'll talk about this coming up. So an alpha particle then is nothing more than like supercharged helium, and you want to be very careful. Now, we've been throwing electrons around since Chem 221, maybe even Chem 151 for some of us. But anyway, this beta particle is really nothing more than an electron as well. But this is also like a supercharged electron. And normal electrons you want to be careful enough with, but these electrons you want to be very, very careful. The energy of these electrons much higher than the regular ones. So a beta particle is nothing more than a supercharged electron. Now, notice this weird symbolism over here. Electrons obviously have no protons or neutrons. So the 0 here makes sense. That's protons plus neutrons. Obviously, there's none. We're going to see why in a while. Electrons get a -1 down there. And that's kind of weird right now, I understand, but just bear with me. The -1 in the bottom shows that you have a beta particle. This is the symbol for beta in the Greek symbolism, and that's sometimes used. So again, alpha particles and beta particles, supercharged versions of what we've seen before. A gamma ray doesn't have any mass, and I shouldn't really call it a particle, but it does go well with this section. So if you see a little gamma right here, this just means a type of energy that's coming out. And gamma radiation, if you remember from Chem 221, is one of the highest forms, the most energetic forms of electromagnetic radiation. We'll talk more about what it is, but a lot of these reactions, when they react, these gamma rays are released, and they can be pretty intense. Now, a proton is going to be a player in this as well. And a proton, if you think about the symbolism, you would have 1 proton in the lower left, so that's where the 1. Protons plus neutrons, 1 plus 0 would be 1. So this is the symbol that's going to be used when we're dealing with reactions with protons. Now, a lot of times it gets the symbol little p for proton, obviously, but really a proton is nothing more than a hydrogen atom. So both of those are equivalent ways to talk about these supercharged protons. A neutron is also a player in these systems. And a neutron usually is just a little n, all right? It has no protons. Protons plus neutrons, 0 plus 1 would be 1. If you see this symbolism, that's what that means. But the coolest one of all, in my opinion, is the next one. And this is called a positron. A positron is an anti-electron. So if an electron is 0 minus 1e, notice down here, 0 plus 1e. This is not a proton, it's an anti-electron. And you can have a beta right there. Now what we're seeing in this section is something that in Star Trek I always talk about, get excited, which is antimatter. And in Star Trek, the Enterprise used antimatter to make the warp engines go. Antimatter is actually a real phenomenon, and we're seeing it right here. A positron is an anti-electron. And if an electron and an anti-electron come together, pretty intense things can happen, just like in Star Trek or these kind of shows when matter and antimatter come together, all kinds of energy. So these are going to be common players in the reactions we're going to see in this section. And you can see why it's different, a lot more energy going on, so we're going to have a lot different kind of pieces. In your companion, you have the nuclear chemistry guide, which basically reiterates these with a little bit more details. Let's see what's going on here.
You're aware that radioactive materials give off energy, especially if we expose this sample to ultraviolet light. We can see it glow. There are three different types of radioactive particle energy. There's alpha radiation, beta radiation, and gamma radiation.
Listen to the clicks in the video.
Here we have a nuclear scaler that measures radioactive decay. Each click that you hear is a nucleus of an atom that is decaying by giving off a radioactive particle. This is a Geiger tube, and it has a window that allows the radioactive particles to pass and records them on the nuclear scaler. What we'd like to do in this demonstration is to test our samples both for penetration and also for the distance that you must be away to receive any protection. Let's place a beta particle in our sampler. We notice that there's a slight increase in the counts. The background radiation is not nearly that fast. Here we have some small sheets of lead that we'll place there to provide some screening. We notice that even one lead sheet dramatically cuts down on the beta radiation. 2 and even 3, and we're down now to quieting the counter back to background radiation. Let's see if that also works for gamma radiation. We'll change the sample. We notice immediately that more energy comes from the gamma. 1 sheet of lead and 2 and even 3 that quieted the beta does not quiet the gamma. We can add even a 4th. Gamma has the greatest penetration of all the radioactive particles, alpha and beta. Gamma is an electromagnetic energy wave. Well, let's see what happens as we go from being close to a radioactive source to far away. We notice that the amount of radioactivity is greatly decreased by distance.
So you're seeing in this video lots of things that are kind of important of this section. First of all, a lot of the reactions we're going to look at create alpha particles, beta particles, and gamma rays. And alpha and beta, as we saw, are actual mass particles. So alpha was helium and beta was electrons. So they definitely have radiation, but if you have to get away from them, if you cover it up with something, that will usually be a good blocker. On the other hand, gamma, which is pure energy, it's like beaming a flashlight, all right? It's literally pure energy, and these are so high energy that it'll go through lots of things. So we'll talk about the types of radiation. Each one of these has different effects and stuff. Sometimes the best thing isn't to wear lead underwear, it's just to run. And I mean that sincerely with no hopeful sense of cowardice around me, but because sometimes distance is the best way to get from these really high energy systems. So we're going to look now at how we can balance a nuclear reaction. And it's pretty simple and stuff. In a nuclear reaction, you have to make sure that the number of protons that go into a reaction equal the number of protons that come out of the reaction. And likewise, the number of neutrons that go into the reaction must equal the number of neutrons that come out. So as an example of what these reactions look like, this is a reaction right here with radium. Now radium was a thing that they used to use on a lot of watches because you could see them at night. Radium though is really radioactive. It's an alpha emitter. It creates alpha particles as it decomposes. And it decomposes into radon. And if you know about radon, this is something they test for in houses. So the product is not really that much safer than the initial reactant. But anyway, regardless of all the sociological and medical implications, this is an example of a balanced nuclear reaction. Now the lower left-hand numbers again, those are the protons. And you can see that 88 on the left equals 2 plus 86 on the right. Cool. The top left-hand numbers represent the mass numbers, which is protons plus neutrons. So you want to make sure those are balanced as well. So 226 equals 4 plus 222. This is a balanced nuclear reaction now, which is kind of cool. This is an example of a type of a problem you might see. Let's say that you have some uranium-235, another powerful player in all this system, and it's breaking down or decomposing into a beta particle, all right? So a beta decay just means that you're going to create one of these supercharged electrons. So what we'll do here in a little bit is we'll find the identity of this new product. Alicia, you had a question?
Yeah, so when we're doing like a normal balance equation, we have to do like coefficients and find them sometimes.
You really, you can, like if you needed extra protons, you might be able to have like 2 alpha particles, stuff like that. But most of these, all right, are gonna be just individual pieces, and you're more interested in the protons and the neutrons without using coefficients. But that is always a possibility. Great question. All right, so in this one, we've got this uranium-235. It's breaking down, and it's breaking down to through what's called the beta decay system. And we want to find what else is being made, basically, in this process. So what we're going to do is we're going to create like a type of reaction like we had before. Uranium-235 will be our only reactant. And then we're going to have on the product side a beta particle, which is what the beta decay means, and then something else. And by deduction, we can figure out what the other piece is. So if uranium if it's uranium-235, we need to know the number of protons. And again, this is something you look up on the periodic table. And good old 92 right there is uranium. So the symbol for it here would be this right here. The lower number is the protons, this number is protons plus neutrons. And this is something you'd have to be given in this type of problem too. So normally, all right, when you're dealing with these kind of reactions, we don't think about the stoichiometry like Alicia said, but that is always a possibility. So in this example then, what's going to happen, it's going to break down to a beta particle. If you look back on the system, this is one way to write the beta particle. And something else, all right? And I'm just going to put the generic representation for this right now. In Chem 222, I would even tell you if you needed to use a stoichiometry. So hint, hint, hint. Good question. So let's figure out what all this is, all right? And again, the idea, the punchline, is that protons in equals protons out. And neutrons in, which we can monitor through the mass number, even though it's really protons plus neutrons in equals neutrons out. So the math isn't too crazy. 235 in the upper left equals 0 plus A, and we'll solve for A. So A here is going to be 235. And we'll do the same thing on the bottom. So 92 equals -1 for the beta particle plus Z. Z, you can add 1 to both sides. Z is going to be 93. So if you look on the periodic table, right next door to uranium is NP. Does anybody know what element that is? Neptunium. Well done. That's right, Neptunium. So Neptunium is the symbol we'll use. And again, we all got that by looking at 93 on the periodic table. You'll always have the periodic table in front of you. So what this says is that uranium-235 here is undergoing beta decay, and that means it's losing a beta particle, an electron. And in the process, we end up making Neptunium-235. And again, what we did here is lower left-hand numbers on the left equal lower left-hand numbers on the right. Same thing for the mass numbers. We found the symbol based on the periodic table's atomic number. Oh, and beta decay. Decay means that you're going to have that thing as a product. So in this case, because it was a beta decay, that means you'd have a beta particle as a product. If it was, for example, a neutron decay, you would have the symbol for a neutron right there. Decay always means product. In the deep part of this uranium, what's happening is one of the neutrons is breaking down into a beta particle and a proton. This is why the beta particles get this 0 minus 1 electron symbol. -1 plus 1 gives you 0. 1 plus 0 gives you 1. Somebody in Chem tutorial, I don't remember who it was, but somebody asked me about the masses of protons and electrons, and they saw it was almost equal to a proton, to a neutron, and it's true. Neutrons are more massive than protons and electrons. Protons are close to a neutron, but still less. And if you add the mass of a proton and an electron together, it's about equal to a neutron, and we'll come back to that in a little bit. But if you're curious, then one of the uranium's neutrons is actually breaking down. It's breaking down into a proton, which stays in the neptunium. That's why the lower number went up, and a beta particle is emitted in the process. So let's say that we have this kind of reaction. This is a uranium-235 breaking down to a thorium-231. And we want to know what the missing particle is right here. Well, what I would do in a problem like this is I would first figure out what the symbols are, all right? And so 92 equals 90 plus Z. What do you think the number Z is going to be? 2, that's right. And I would do the same thing on the top, although you probably figure it out now. But anyway, 235 equals 231 plus A. So what is A equal to? 4, that's right. You can find the symbol for X if you look on the periodic table. 2 is what you'd use. That's the helium particle, the supercharged helium. Nobody usually calls it, though, helium on this level because it's quite different from the helium from birthday parties. People will usually call that supercharged helium an alpha particle. So this reaction is uranium-235 undergoing alpha decay to create thorium-231. Question? Emission and decay are used to show when a reaction is creating a particle. So if you hear emission or decay, like beta decay or neutron emission, whatever it is that's decaying or emitted, it's going to be a product particle. So this is an example, this is an example of a positron emission. So emission means, again, that something's going to be a product, all right? This is the symbol here of the positron. It's an anti-electron. So in this reaction, this is a polonium-207. It's undergoing a positron emission to become a bismuth-207. But again, the important part here is that emission or decay means you're going to have that thing as a product, and you can figure out usually what the other remaining piece is then from there. Once in a while, you'll hear about capture, all right? And this is especially used in neutrons, but sometimes beta particles too. If you hear about a capture, that means that that particle is a reactant. So a neutron capture reaction would have a neutron as a reactant. This is fluorine-19. It sometimes captures a neutron to become fluorine-20. Neutron capture is the most common, but there are other kinds of captures. Most of what we'll see are emissions and decays, and again, it can be decay. That goes right there on the product side, all right? But on the other hand, if you hear capture, all right, then that weird thing goes as a reactant. Cheesy sound effects, sorry. Questions?
Do you have a gamma capture or a positron capture or anything?
Positron capture, definitely. I don't know of a gamma capture, but I wouldn't put it out either. Positrons are a type of antimatter, and if you're at all interested in science fiction, which is my core world of that. Anyway, antimatter is a big thing. In the formation of the universe, all right, there's all these theories about matter and antimatter, and it's really cool stuff. But this is something we can totally see in this particular example. Dirac was the person that figured out about the spin quantum number in Chem 221, and if you don't remember, I would hardly hold it against you. But anyway, he was the first one to predict antimatter, 1928. And at first, people thought, well, maybe, you know, but actually there's been a lot of examples of this, and they're trying to think of it as an energy source for spacecraft and stuff like that. But anyway, the one we're going to focus on here a lot is what's called the positron. And if you have matter and antimatter, they come together. And if you look at the numbers here, -1, +1, 0, all right? 0, 0. So 0, 0 thing means you're going to have a gamma ray. And there's a lot of energy released. So in like Star Trek and these kind of things, or Doctor Who did this a lot too, you know, the matter and the antimatter. Sound effects not necessary. Anyway, the is in my science. Sorry, this is really dark. The explosion is represented by gamma rays. Gamma ray has a lot of energy, all right? And so the gamma rays are the way what happens when. And anytime you have matter and antimatter, there's antiprotons and all kinds of cool things. But you can see once again that lower left-hand numbers on both sides are equal, upper left-hand numbers are the same. This particular one actually has a very practical thing. Positron emission tomography is something they use up at OHSU for detection of things, and it does use these antiprotons, these positrons, which is pretty cool. This is another example and stuff like that of how this is going. Neutrino is another one of the really small things, much smaller than protons and electrons. But a neutrino has an anti-neutrino as well. And sometimes the anti-things get little lines over them. This is going into physics. They call these annihilation reactions because there's so much energy given off. And it doesn't matter what matter and antimatter pieces come together, you always end up with gamma rays. And notice that 2 particles in mean 2 gamma rays out, and that's also part of physics. Just realize it's something we have to pay attention to. Neutrino is something they're still trying really hard to detect, and they think they've got these big underground water deposits and stuff. And Pauly, another person from Chem 221, was the first person to predict a neutrino existed. If you're planning on going into physics, Dimitri, then this might be something you'll see more of, man, and it's really exciting. This is kind of a 21st century, really exciting area in physics, in my opinion. Yeah.
And the positron, the negative charges are basically the 2 same particles. It's all about the quartz.
Yeah, that's a good way to think about it, man. Absolutely, right on. Uranium-235, I showed you two ways that it decomposes. One way was through a neptunium, and one way was into a thorium, and all of these things are possibles. So a lot of times in nuclear chemistry, you'll see something that looks like this, and this is called a decay scheme, like how this particular molecule or atom breaks down. And this one right here is for uranium-238. And so this is like literally each of these little dots is like a step. So here's uranium-238 decomposing to thorium-234. And you'll see by the top numbers there's a difference of 4. This would be some kind of alpha emission. And then it goes through a couple of things to get over here to uranium-234, and then another alpha decay, and another alpha decay, et cetera, et cetera, et cetera. And scientists have studied these things in a lot of detail, so they create these kind of pieces. Oftentimes with the heavy elements, lead is kind of the end point, like where it stops, where they're stable. And that also means then that everything up until then is unstable. And along each one of these pathways, it's probably going to be an exothermic reaction, some kind of energy is going to be given off. And if you have one of these, you can literally figure out the individual steps and stuff to see what's happening. Another thing you're going to see in nuclear chemistry is what they call a metastable nuclei. And sometimes when you have an atom and it's been energized by these gamma rays, you don't have a good mixing of protons and neutrons. Now, what we've seen so far in our classes is that the electrons sometimes, if you blast them with energy, they'll start emitting different things. And in Chem 221, the hydrogen spectrum lab, that was all about electrons jumping up and down between the levels, all right? Those are the electrons being excited. And so electrons, when they're excited, usually give ultraviolet, infrared, these kind of frequencies and stuff. But the nucleus, when it's excited, it's a whole nother energy gamut, all right? Because to make the nucleus get excited takes a lot more energy. Now, on a practical level, if you're having a problem thinking about metastable, you can think about protons and neutrons in the nucleus, and they're mixed up really well. So when I'm making a peanut butter and jelly sandwich, I put the peanut butter down first, I put the jelly over it, and it's nice distribution, like I don't have more jelly on one side than the other. That's the normal way that the nucleus is for protons and neutrons. But if you see a little M, like you're seeing there on the left-hand side, if I was making a peanut butter and jelly sandwich with a metastable version, I'd have like all my jelly on one side of the bread and all the peanut butter on the other side. And that's not a real stable way. I mean, okay, yeah, you can smash the sides together. But anyway, I'm getting hungry now. Anyway, that's not the normal way. It's best to have all the peanut butter and the jelly kind of mixed together. So metastable, all right, just means that those neutrons and protons, they're not mixed well in the nucleus. That's a practical way to think about it. Now, in reality, it's more complex. You've got spin states and stuff like that, but it's not as much fun as talking about peanut butter. All the metastable states are going to break down to their normal state. So this is an example of technetium. That's a common atom that's used also at OHSU. They can excite it to a metastable state. That's when the peanut butter and jelly not mixed well. And that technetium wants to get to the place where the peanut butter and jelly are mixed well. And in the process, it's going to release that extra energy, almost always as a gamma ray. Once in a while X-ray, which is right close to gamma ray, but most of the time it's gamma. So much energy. You have no change to the protons or the neutrons, so the numbers stay the same. You just ditch the M on that side, and you end up with a gamma ray on that side. These are really helpful. Medical imaging, again, is where a lot of these things are really helpful. So you've got, they want to probe your body for some kind of thing. A lot of times these gamma rays will be, these metastable states, will be sent in, and as the gamma ray is released, they can detect it in a detector. It's pretty cool. So, punchline, if you see something with an M, it's just going to break down to the normal version plus a gamma ray. So that leads us to something now where we're definitely going to be kind of having one foot in physics and one foot in chemistry. And to really make sense of how all this stuff works, I need to talk about the 4 forces of nature. And some of these are really useful in chemistry, but the first one, gravity. Gravity is one of the forces, and really it's not something that we've dealt with that much in class. It was what kept our mercury barometer, all right, from the mercury like going crazy up to the top. The gravity pulls it down, but most of the time chemists don't worry too much about gravity. Gravity is a really long range force, all right? So it holds like Saturn to the sun, it holds our solar system to the galaxy and stuff like that. But it is a relatively weak force compared to the other forces we're going to see. Gravity is not seen as that strong. Now, there is a type of force in the nucleus called the weak nuclear force, and this is more a force that's used by physics. It's not very strong compared to the two we're going to talk about in a second, but a lot of the beta decay reactions we're going to talk about actually use this. So these are two of the four forces of nature, but the ones I want to talk about are the electromagnetic and the strong nuclear. Now, electromagnetic, I've been hitting you with since the very first day of Chem 221, because that's the positives and negatives, the handshakes with all of you that have been down here in the front row, all of those things about positives and negatives coming together. And you mix them well, and they're pretty strong, makes good bonds, ionic, covalent, hydrogen bonds, all those kind of things. Those are pretty strong force, all right? They feel that EM, electromagnetic, is about 10 to the 36 times more powerful than gravity. And again, we've seen this a lot with, again, electrostatics, positives, negatives, coulombs, all that kind of stuff. I am not qualified to tell you how they calculated it was 10 to the 36 times more powerful, but I'll take their word for it. Just what you need to know is that EM is stronger than gravity and the weak nuclear. But there's one that's even stronger than that, and that's called the strong nuclear force. Now, in the atom, you have a whole bunch of positive protons sitting next to each other, all right? That's going to cause repulsion by EM spectrum, the electromagnetic force. The electromagnetic force says that opposite charges repel, all right? So having a bunch of positives next to each other, bad call. So the strong nuclear steps in to kind of make that possible. And without it, we wouldn't have atoms at all. Now, one of the ways that strong nuclear helps is by the addition of neutrons, all right? Neutrons tend to dilute the positive protons from each other. So if two people are fighting, I can step between them, hopefully make a little bit of a barrier. That would be like the job of the neutron in the nucleus. Strong nuclear is about 1,000,000 times stronger, they tell me, than the electromagnetic. So electromagnetic was already strong. Strong nuclear is even stronger yet. But the strong nuclear, very short distance. 10 to the minus 15th meters, that's a femtometer, and that's much smaller than the types of things we looked at in the solids lab. We looked at picometers and angstroms. A picometer is 10 to the minus 12. Strong nuclear only works about 10 to the minus 15th. So if your pieces are very, very close together, i.e. the protons and the neutrons in the nucleus, the strong nuclear helps to keep them apart, keep the nucleus stable. I would argue that the glue that holds the nucleus together is the strong nuclear. The type of glue that keeps the atom together would be more about the electromagnetic, those negatives and positives kind of holding together. So what you see up here are all the types of ways that everything in the universe, according to science so far, everything in the universe uses to keep things together or push apart, all right? Gravity, really important, obviously. Planets, all of us are sitting down, not floating on the ceiling. Weak nuclear, not as cool, but it does help with some types of breakdowns. But these are the two I'm going to talk about here. Why are you going to talk about it, Dr. Russell? Oh, good, whoever asked that in the back, front. No, just joking. All right, you're all looking at me like, oh, God, I'm going to get out of this lecture. All right, Prophet, back on. Why this is important, all right, is that you've all heard, around uranium, Homer Simpson, right? All the dangerous stuff in the nuclear power plant. Well, that's because as the atoms start getting bigger, they can start to decay, all right? And I will argue, all right, that nuclei begin to break down because They get so big, that strong nuclear no longer can keep the protons apart from each other, all right? And when that happens, then you're going to start to have the atoms break down into gamma rays and stuff like that. Now, atoms will try to compensate with the EM force to not break their atoms down by doing what's called magnetic dilution, and that's adding even more neutrons to make the atom more stable, all right? And that will help to a point, but after a while, you just don't have enough pull from the strong nuclear to keep them apart. So if you look at the periodic table, and you look at all the red numbers up there, up to about calcium, roughly, all right? The red number is about twice as much as the blue number. And calcium is a good example of that, all right? 20 protons, the red number for calcium about 40. The most stable isotope has 20 neutrons to it, all right? And helium is about 4, and it's got 2 protons, so again, twice that number. Roughly, that's the most stable form of helium. However, there are some exceptions, by the way. Once you get past calcium and up to lead, then the most stable nuclei are going to have more neutrons than they have protons. So, for example, we talked about copper earlier. All right, copper is, we'll say 63. Well, 29 times 2, 58, that's less than the 63, the most stable one. And that shows that copper is pushing extra neutrons in, trying to keep those protons a little farther from each other, so the strong nuclear force still has a chance to keep the atom together. But once you get past lead, this is uranium and this is americium and all these things, you can argue that all isotopes are unstable and radioactive. And these are the ones that you'll see in a lot of the big nuclear plants and stuff. Now, this is a graph that demonstrates what I just told you. And I want to talk about this a little bit. The y-axis here is the number of neutrons, and the x-axis is the number of protons. And this black line right here would be a slope of 1, where the neutrons and the protons are the same number, all right? And you can see that roughly up to about calcium or so, all these dots, which represent the isotopes, most of the dots are focused right on this straight line. But then you start to see a gradual shift away from the slope of 1 line. So if you shift to the left, that means you have more neutrons relative to protons. And the black little dots in the middle, those are the ones that are truly stable, all right? The red ones around it are the ones which are going to be radioactive. They're the ones that are going to break down into gamma rays. So people with a little bit of creativity have come up with this idea how the black dots represent a peninsula of stability. So peninsula is like a part of land that juts out into the lake and stuff like that. This is our peninsula, the black dots of stability. And around the peninsula, around the black dots, you see a ton of red dots. That's the sea of instability. It's all the isotopes which are going to break down one way or the other. The ones up here on the left usually undergo beta emission. The ones over here to the right are going to be more alpha emission. Down here you've got positrons and stuff like that happening. But this is something that they talk about sometimes in nuclear chemistry. There is a sea of stability, very stable elements, and all around it is the sea of instability, the unstable isotopes as they begin to break down. Now, why I find this so cool is that on one level, kind of feels like the number of stable isotopes is limited. However, two of the real big names in this field, one guy is Glenn Seaborg, we'll talk about him more, and then one of his graduate students who became his own research person, Ken Moody, believe that once you get past this little sea or a peninsula of stability, there are going to be islands of stability further on. And again, I am not qualified to understand why they're coming out this kind of stuff, but they've done some research and they think that one day there's going to be some islands of stability where there's atoms with like 200 protons. all right, and they're going to be stable. Right now, the ones down here, the clear ones, those are all the radioactive ones. They exist for like 10 milliseconds at a time. But the hope is that one day there's going to be these cool, really heavy atoms out there which are stable. So they call it islands of stability in a sea of instability. We're kind of at the end of our peninsula of stability right now, and the sea of unstable isotopes is all around us. But there's a lot of people that think there's going to be an island of stability coming up. So, okay, getting a little excited there. Yeah, questions?
Will that be like more powerful energy or something like that?
Who knows? I mean, this is where now, as a scientist and my love of science fiction really collide, so I'm going to let you know that right now. But you could have something that was super dense, for example, might be really good shielding. Maybe there would be higher energy. Honestly, I don't know. So, knowing that, and knowing that we've kind of reached the end of our peninsula of stability, you can begin to make predictions as to how the different isotopes are going to break down. And this is just one graph of many, but anyway, if you have more protons and fewer neutrons, a lot of times this is where the positron emission will kick in. Sometimes you'll have a lot of neutrons relative to the number of protons. Those will be beta decay. And the heavier ones, if you had to make a guess, most of the heavier ones will undergo alpha decay, which is that superpowered helium particle. So these are just some examples of things you could use to predict. And I wouldn't make you think like, how will this thing decay? All right, that's more than we need to get into. But I do want you to see some of the patterns. Heavier atoms, things usually beyond lead, most of the time will undergo types of decay. Over here would be a beta decay. This atom has a high neutron to proton ratio, all right? So if you think about neutrons to protons, it would be like that. You can also have low neutron to proton ratios. Nitrogen is usually nitrogen 14, so a nitrogen 13 is an unstable version. They will usually undergo positron emission, or they'll like to capture electrons, which is the same thing, as you'll figure out. But then if you have to make a guess about things past bismuth, I mean, more often than not, they will be alpha decay. That's going to be these guys over here, and there's a lot more of them. Now, sometimes you're going to have beta decay. But if you study nuclear chemistry, these are like ways that the atoms will react. And we saw in Chem 221 how there's like acid-base reactions and precipitation reactions and gas-forming reactions. These would be like equivalent, if you will, in the nuclear chemistry world. So you can actually figure out the energy required to overcome the repulsion of protons. And it uses a combination of strong and weak forces. And remember that the strong forces are definitely stronger than EM, and they're basically all more powerful than gravity. There's a system to find what's called the nuclear binding energy, E sub B. And this will estimate the force contribution to the atoms, like what makes the atoms stay together. And the definition of binding energy is a little weird. It's the negative of the energy change if the nucleus is formed directly from protons and neutrons. So if you imagine if you had like helium-4, you would say, well, 2 protons and 2 neutrons make helium-4. Whatever energy is used to make helium-4, E sub B is the opposite of that. And if that's as clear as mud, I completely understand. Let me show you an example. Let's make deuterium. Woohoo! Deuterium is an isotope of hydrogen. Sometimes heavy hydrogen is the term that's used. The official name is deuterium. Deuterium has the symbol of hydrogen, but it has a 2 right there. And that just shows that it's not just a proton, there's also a neutron. So we can use this reaction to find the binding energy of deuterium. Now, if you look at the mass of a proton and the mass of a neutron and you add them together, and these are things you can, use the all-powerful Google for, it's not the same as the mass of a deuterium, all right? Deuterium 2.014 is not the same as 2.016. And at this point, as a chemist, I start to get nervous because all the time I've been making you balance chemical reactions. Mass that goes in, mass that goes out. Something's wrong in the nuclear chemistry world. Mass is not conserved. And that means that the mass that goes in this case, is greater than the mass that goes out. This is the mass differential, the mass lost upon making the deuterium. So thank heavens, Einstein came to the rescue. And Einstein's E equals mc squared, or the full version, delta E equals delta mc squared, we can use to figure out this energy. So let's take that little delta M on the last slide, which was in grams per mole, and I need to turn it into kilograms. So this is a smaller number by 10 to the third because I converted grams to kilograms. And I'm going to multiply it by the speed of light squared. C 2.998 times 10 to the 8th is the speed of light. And we get this just incredibly large number, which is a 10 to the 11th. That's the joules per mole, all right? That's the energy here. And if you do a little bit more with it, the binding energy is the opposite of this number, all right? It's a way that scientists have made the number positive. So you get this 10 to the 8th kilojoules per mole. And this is kind of a cool number because it shows why deuterium wants to form in the first place. There is an energy X that's being released upon making deuterium from protons and neutrons. And all atoms, if they're made, are going to have an exothermic value. This is justifying why atoms form at all. Like why they don't just stay as individual protons, neutrons, and electrons. You actually get a lot of energy out, and the opposite of that is the binding energy. I need to stop here. We'll take this up on Monday. Have a wonderful week.